Our string.
It's not on there.
It is not on. Okay. Oh, yeah. Thank you. Okay. I'm going to try to. We'll think I don't want to watch, because that's no good. But we'll be, yeah, trying to go through. Stop me if there's questions, because like it doesn't do anybody any good if I'm going and people are watching, right? So give a shout, and we'll see where we can go. So I want these negative value decomposition. Let's see. How many people have been exposed to SVD, and how many people know what SVD is? Okay, good. So here's our statement of the inverse problem, and yeah, we're going to try to solve it. We've seen this equation before, so that's our linear integral equation, and we've got this system here. D is equal to Gm, so G was our kernel functions that have been done. K is an n by n matrix, so it's underdetermined. There's a lot more variables, so there's infinitely many solutions. We've seen that it's not only undetermined, but it's also ill-conditioned. And then what I want to do with SVD, and this is why it's so nice, is that it just illuminates the fundamental aspects of that inverse problem and why they start this table. So we saw this particular example before. So let's suppose that we've got Gm is equal to D. Then really what we want to write is G minus 1, right? So we somehow want to do M is equal to G minus 1D. But of course, that doesn't exist, right? If you actually typed it into your computer and tried to kind of solve this particular problem, you get out some kind of an answer, but the computer is actually doing something behind the scenes to do. So you can actually try this. Take whatever language you're doing and write Gm is equal to D, but just with this one datum problem, and just see what you get out. Be interested, because you might not all get the same solution out. So what singular value decomposition does is it takes the matrix G and it partitions it, writes it in a factored form of U lambda V transpose, where the matrix U has got P columns, U1 to UP. So these are going to be the effectively eigenvectors of data space. Lambda P are a set of scalars, so this is diagonal elements. So these are called the singular values. And VP are basis vectors for model space, and yeah, they look like this. So lambda is the singular values, V are the vectors for the model space, and these vectors are orthogonal. So if I take one vector and do an inner product with the other then I get the identity value. And similarly, the eigenvectors for U are also orthogonal. The interesting thing about this is that if I start with a vector, well, if I start with a vector vi here in this space, it's actually connected with a ui here. So these vectors u and v, they're just intimately connected, and the matrix G is the thing that connects them, as well as the singular value lambda. So if I take a vector vi in here, I multiply it by G, then I actually end up with that vector here. So v1 here goes to u1 here, and then multiplied by some lambda I. And then when I do the transpose, I end up, if I start with the ui here and the G transpose to get back in here, again, I'm connecting u1 and v1 with this lambda. So that's the thing with singular value decomposition. Remember, we've got data space, we've got model space. The singular value decomposition kind of connects them. So one vector here connects with one vector here. That's just a real tight connection. In here, we're going to divide model space up into two parts. One is what we call the parallel part, which is the activated portion of model space. And the other is the perpendicular part, which is the annihilated space. Our data are connected only with the activated space. The data do not tell anything about. I take any element here and further multiply it by G, I'm going to get the zero value. So how do we solve a problem using singular value decomposition? And in fact, there's quite a few inverse problems that have been solved this way with a generalized inverse. And so that's functionally good, but it's also good in what it tells us. So here we just have to go through the algebra. So we have Gm is equal to D. And now I've got this representation G is equal to U lambda V transpose. So I put that in here. Okay? So that brings us to. Now I'm going to multiply by U transpose. So remember, U transpose U was an empty, so that cleans out this. And then I get U transpose V. Now I want to get rid of the lambda. So the lambdas, the singular values, I neglected to tell you, are all positive. So that's why I have a subscript P that there's only P of these vectors. Those connect with positive singular. So I multiply the lambda and so on, and I get this equation here. Okay? So I'm almost to M. But the best that I can do is do a V times V transpose. So now I multiply by the matrix V, and I get something that looks like this. So what we've done here is we managed not to actually get M, but we got a V times V transpose. And we're going to say, okay, guys, that's our solution. And we're going to call it, that's our constructed solution. It actually is that part within the aggregate part of the data space, and it's equal to the true M multiplied by this, and it's given by this term. Okay, so often you'll see, G M equal to D, and somebody will come along and say, oh, here's a generalized inverse, and so MC is equal to this guy. Okay, so now we take a look to see, okay, what is that? That's matrix, right? But let's just maybe do it in terms of vectors so that we've got a bit more of a handle. And if we write this out in terms of vectors, it's the same as doing a sum of each eigenvector ui onto the matrix or data vector D. divided by lambda. So that's a coefficient that I'm going to multiply the basis vector in model space by. So B. So what we see is that the final solution, remember the number of these eigenvectors VI in actual basis. The final solution is actually going to be a sum of these. And the sum, or the coefficients, are going to be given by 16. So each eigenvector is scaled by this value, and you notice that it's divided by lambda I. And that means that if the singular value happens to be something that's very small, this approaches something that's big, so that particular vector is going to appear a lot. So what we're going to do is to look to see how we actually build this. So our constructed solution is a linear combination of these with these kind of scalar multiples. And we're going to look to see how that happens. When p is equal to 1, we take the largest singular value. We're going to have a particular misfit, and we'll have a particular value of more. And as we increase the values of p, we're going to get better and better solutions. But that's also going to increase the model. So we talked about this thing being ill conditioned. Look what happens here. So our constructed model is this combination of vectors. And the very first eigenvalues, or this is our point example, this one is 0.13, and the first eigenvector in model space looks like that. So it's it's a very smooth function. And then the amplitude by which I'm going to incorporate that in the solution is given by this value here. If I look at the second singular value, now, so this one's 0.13, this one's 0.11, so it's not much more. But notice it's got more structure, it's got 2 zero constants. And the third looks like this. The 11th looks like this. And the 19th one goes chuk, 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 chuk. Okay, so these are the vectors. Okay, so that's what you've got to work with. Your final solution is going to be a linear combination of those guys. If you just go ahead and compute that as the linear combination, then you get these coefficients out here that are going to be responsible for how much you're going to add inputs. And what we see is that when we have very small singular values, then the sort of the amount that we add in, so we're going to heavily use those guys. But if we and if we gradually increase the number of singular values, the amplitude by which these things come in starts to increase. So let me break one more thing down. What we've got here on this column is the true data. So if you just have the true data, no noise, then the amplitude that I would add this big singular value in small singular value is about 1.7. If I keep the noise that was added, because the observed is the true plus the noise, then I'm over in this column, and the amplitude of the signal now becomes really astronomically large. I think this is 10 to the 13th. So when I'm trying to add these components into the solution, I'm multiplying this particular eigenvector here by a factor of 10 to the 4, and this one of 10 to the 13. Right? So there's, if I include that particular singular value, all I'm going to do is bucketing up or down that is coming from this particular argument. Okay, so clearly, some of these guys are causing more harm than they are good, and that leads us to this thing. So now we've got our singular composition. Our constructed norm is linear combination of these vectors, and then some of them, are just doing more harm than good. We've got noise that's in the data, and that's just causing a lot of problems. And therefore, the best thing to do is kind of truncate this at some value Q, and that means that we're not going to be exactly the space here, but we're going to do just some portion of it that's spanned by Q eigenvectors. So here's what happens. So with our truncated SVD, if we have just if we go to the third vector, by that time we get up this kind of solution. Go to the fifth vector, we end up with that. The sixth, we end up with this. And the 19th, we end up with this. So up until this position here, we're actually doing a pretty good job. So we're happy to take all of these vectors up to 6, and that's doing a pretty good job. But any of these others, they're actually more affected by the noise than like doing us more harm than good solutions. Just truncate. Okay, so yeah, maybe plot this. So what we're looking at here, so here's that. It's kind of a Shannon curve, and that's a misfit because it's smaller. And Q is we end up with something like that, so we're right here. And Q is before we're down here, right? So it's good. And Q is equal to 5, we're better than the misfits, we're here, and Q is equal to 6. Okay, so it's kind of like adding, changing the beta type of thing, so we can kind of understand where this blow up of the noise is coming by including these singular vectors that have along. And in fact, there's strong correspondence with the with the key constitution. We can actually show that by truncating SVD, we can get essentially the same solution by just doing a modification of the weight for the SVD. Yeah. So here's the takeaway message. Here, so if we've got this T-graph curve that we had before, where we were solving, so where we're solving this guy. This is what we had when we were solving the T-graph curve. We had this. If we now went to the truncated SVD, we get almost the same kind of curve. And yeah. So there's a couple of reasons for doing that. So here's the summary. So we've got this matrix G that kind of connects model spaces in the data space. So our symbiotic composition was like this. It had up to P of these. So these are non-zero values. We can either just sort of truncate these guys, so just go to Q of them, or we could introduce an extra multiplying coefficient here to reduce the effect. But irrespective, you have the same kind of thing that's happening. So, what does this tell us about the inverse problem? I mean, we used to think it was bad because we only had, let's say, in our toy problem, like we had 20 data. So that means that our activated model space is actually pretty small. But now we understand that because of the noise and the singular value structure of the matrix, it's even much, much smaller. Yeah, so that was the point of that. There's another important point that may or may not resonate with you at this time, but will come into play, and that is we end up always trying to solve a matrix system, and we're really solving that using techniques of conjugate gradient. How many people have done? Does anybody know what a conjugate gradient solution is? Okay. Anyway, there's different techniques that you can use to solve systems of equations, and doing 10 iterations is kind of like taking the effects of 10 singular factors here. So there's connections there with how we understand what's going on in the SVD formulation with many practical aspects of what's going on. Okay, so that's the purpose of that is just to really consolidate your understanding. And now let's go back to the next one and do the linear problem. Any questions while we're changing things here? Okay. Okay.
Next is something that,
Please.
so do you have a way of putting an SVD diagram to work with a full G matrix? I'm just thinking for really, really big problems, you still have to process the complete G matrix to get your singular values, right? Or is there a trick that where you never work with a complete G matrix?
Well, we do work with complete G matrix, but we tend not to actually do the SVD decomposition on that, but actually solve these, now we're coming back to conjugate gradient solution. But then because you're doing conjugate gradient solution and you're continually doing your iterations, then you can kind of think of the result that you're getting out as being, oh, that's like the first and. So I think that's the other place that the SVD solution kind of adds some insight into what's going on.
And we're never forming G matrix.
I'm sorry?
We're never forming G matrix.
No, well, that's the thing, right? You need to know if you're going to get singular values in a standard SVD.
Right. So if yeah.
So you cannot send it to computation state.
Well, I mean, in some cases we do. Like here, we have G, but in other cases, when we talk about bigger problems that they'll show later, yeah, we can't even generate the sensitivity matrix. Right? It's just too big. Okay. Here is a. I'd like to talk about the L2 norm, and so we're going to set this up. And then to kind of investigate the details. And we have two apps. There's the 1D inversion, which we've kind of shown you. And then there's also an app for the 2D crossword. And what I want to do is now we're going to kind of step forward and try to start to incorporate additional information. Some alpha parameters, reference models, and then we'll use the 3D magnetics. So what we're going to do here is keep sort of a generic solution using L2 quadratic functions, but then gradually bringing in, okay, I need to incorporate this information or that. How do I do that? So here's our linear example. Here was our G, M, and D. And we have a mesh that was just uniform divided region 0 to 1 into 100. Crossflow tomography, as I mentioned before, we've got a well-specified transmitter. Here's our receivers. And we can put a block in here. Actually, if you could put multiple blocks, and you could raise them around, you can do all kinds of things. So yeah, it's kind of fun to work with. But I don't think we'll have time to delve much into that. So we'll kind of stay with this. So here's our velocity model. And if we did the crossflow tomography, we measure travel times. So here's the transmitter, here's the receiver. That would have a large travel time and a little bit of anomalous structure because it went through the block. And we plot the travel times on this map here. This is the transmitter, and this is the receiver number. And we get something that looks like this. So there's a little bit of a low in here. This is travel fast. The magnetic susceptibility, is there anybody who doesn't, is there anybody who doesn't know what magnetic susceptibility is? Good, okay. So, let's suppose we got a block in here, magnetically susceptible, we've got an earth field that's coming in here, got a 3D mesh, and our forward problem is linear. So GM is equal to D, and our magnetic data are looking like this. If people remember, we got a block that's magnetized, so it's got an anomalous field, but our anomaly, magnetic anomaly, is just a projection of that anomalous field onto the projection. So that's what it looks like. Let's go make it over here. And here's our chart. So we saw this before. We've discretized here, and we've got two things. One is choose this function, and for that, we're going to have to contend with the noise. So I just want to make a couple of comments here. So our observations are the true forward modeling plus some noise, and we're going to try to find it. The thing that you have to recognize is that you're going to have a mathematical operator to do the forward model. But that actually may not be quite right? Because first of all, maybe you're wrong in dimensions, like it's a 2-dimension, you're using 1, or 3, you're using 2. So your operator here, okay, that you're going to work with to actually solve your problem might not be right. And that's actually going to give rise to errors. Those errors are probably not going to be Gaussian zero mean. They're going to be biased and highly correlated. Nevertheless, just always keep that in the back of your mind that when you're talking about the inverse problem, your uncertainties that you're going to put into the inverse problem have to take account of everything. So it's not only repeatability, it's not only just additive noise, it's everything that goes into that forward modeling. Sometimes people forget this. So it's really important to kind of remember that the noise that you're going to work with is just everything that includes your whatever modeling errors that you've got. And then, of course, you've got additive noise, so that at the end of the day, you've got your observations, and now you've got however you are approximating your forward modeling operator box. That's your thing, which in some cases might be pretty good, in other cases it might have some problems. Plus some noise, which is modeling noise plus additional noise, whatever. But that's how we're going to do it. And at the end of the day, after all of that is done, as a first shot through, we're probably just going to assume these guys are Gaussian with some uncertainty or standard deviation attached. But always remember that you might have some biased errors that are coming in from your model. So the good news about that, that is true, then our misfit representation is chi-squared statistic. So we've got some squares, random variables with zero mean and standard deviation. So the expected value should be n, but then it's statistical, so it could have a standard deviation, plus or minus the square root n or square root 2. So here's the crucial steps for the misfit function. We're going to use the L2. And then we're going to introduce a matrix W, which is a diagonal matrix, and value is 1 over the standard deviation of each data. And then we can write the misfit in this particular matrix form, where WD is this matrix here, minus the third thickness norm, and we have an expected value of this to be something in the order. I said before that we need to put something in here. So you just got to do your best. There's like, okay, a percentage of the value plus the floor. You might choose to adjust that at some point later on. There's a whole bunch of things that can come in, but do something that's sensible and see how that works. So that's the misfit. Then we got the model objective function. So what I want to do is look at one problem, toy problem, and then we'll look at discretizing things and then the role of those alphas. The model marks we showed these before could take many different forms: smallest with a reference, smoothest, or some combination. In general, you're probably going to want to have some combination. You want to have something that's maybe kind of close to the reference model, but you don't want to make that the only criterion, because you also want things, that are kind of smooth. So the way to accommodate that at this point is just to add these things in, but now you've got a few hyperparameters to adjust. But we'll look at the whole. And now if we take that and we discretize it, then we end up with something that looks like this. So now this is a matrix vector system, right? So this is just a vector, it's a matrix, and you've got a system there to be solved, and it's actually a quadratic system. It just depends upon some things. So now we'll perform the inversion. So we've got our misfit, we've got our model objective function. So let's just use small at this point. We can combine everything. And that objective function is quadratic. Just in one variable, it looks like this. If it's multivariable, it's just a big hole in hyperdimensional space. So how do we? What's the defining quantity or defining thing that would indicate that we are at a minimum? Anybody? The grade is 0, right? So the minimum of this is at this particular point here, and you can see that the gradient is equal to 0. So how do we find that? Well, we've got this thing here. So let's just differentiate it. So we just differentiate this to get the gradient. So G is the gradient. So it's grad phi. And if I differentiate this, I end up with a system that looks like this. But if I differentiate that, then I get a matrix well, I differentiate this, so I could get 2 that pass below that, and G transpose affects this guy here. I put it all together, and then I get a matrix now, matrix system that looks like this.
So that's the gradient.
So that's the gradient, and we want that to be equal to 0.
So in this,
That's really easy, right? So we just take this, we make it equal to 0, and then on the left side, we've got this quantity here, which is multiplied by m, is equal to this over here. So we've got a matrix, and then we've got a vector system here. So we can write this, if you like, as A is taking big mirrors here, call it A, AM is equal to B. This quantity is M by M, so it's number itself by number itself. And it's full rank. And we can go ahead and solve this. So this is a well-conditioned matrix. It's full rank. A minus 1 actually exists to the whole bunch of good is you can actually go ahead and solve this. And what that means is that irrespective of where you think you might start, or start at 0 value, for instance, you can get to the solution in one step. So that's the nice thing about L2 stuff, right? It's all quadratic. You want to minimize it, you go to the bottom of that formula once. So now we did one fine tuning on the size. That was okay. Yeah. So here it is. Okay. So let's talk about the role of beta and sort of which beta to use. We've kind of already done that, sort of minimizing this combination and want to find a value that puts it someplace in a reasonable place on this economic curve. If we look at solving systems at different values of beta, so we've got, we're minimizing this, different values of beta. If we start with beta low, okay, then I can start with beta high, okay. So now we're kind of emphasizing this, then the beta high will give us a misfit that's actually really quite high, and a normal norm that's low, and will put us up over here. Yeah. Okay. We get that up. These are reversed. Sorry. It's not a fake. Okay, so beta high is going to put us up here, beta low is going to put us down here, and we want that someplace. So how do we solve for beta? This is the problem that anybody, if you write any paper or text or something on inversion, something goes, well, how do you choose beta? So it's like if you can't think of anything else to ask, that's always a question you can ask, because everything kind of depends, your solution depends upon what that parameter is. And how you choose it is not a trivial thing nor cut and dry, especially when you come to field problems. There's 4 ways that you could generally kind of approach this. I mean, you can just guess and then see what you get out, right? That's possibility. You can do what we did in the app, maybe let's just pick a range of data. And often you can't even tell like what the order of magnitude of this thing is. Like sometimes it should be 10 to the minus 3, sometimes it's 10 to the plus 3. So you could have to experiment your way in on trying to figure out what's a reasonable range. But then pick 3 or 4 orders of magnitude or something and just solve it, see where you are. So what we did here in the app was to do 8 orders of magnitude or something like that. So we did that, and then we chose one that was sensible. Either they missed it, or at the corner of that bell curve. There's other things that you can do, or generalized cross validation. That's a technique used. Another way, we're going to employ this later on through the course as our problems get tougher, right? We're actually going to use a cooling technique. We're going to start with high beta, and then as we keep a curve here, yes, we're going to, especially H, as we start with high beta, we're going to be up here, and we're just going to kind of cool beta, and so, and we're going to quit when we're kind of good enough. So that's what we mean by the cooling strategy. And then we're going to evaluate the results, and then so now we want to evaluate results. The question is, what should I use? Well, the global mixture is certainly one thing. The T-top curve, you generally want to plot it. And then we look at the model. And this is always the case when you're working with realistic data, because you don't know where to stop. So you're going to have to find solutions that have from a number of different values of data, and then always look at the resultant model that you get, and assess, is that too much structure or not? So there's some subjectivity that's going to come in. And then also the normalized misfit. That's the other thing that's really important. How well are you fitting the data? Sometimes you can identify outliers that are there, and if there's problems with the data. And then also looking at other models with as I said, with different data can be helpful. And then once you looked at this, you can make some decision about, okay, do I want to change something, or am I good to go? So in the app, we have a couple of things that you could work with. So here is the observed and predicted data. And remember, if I had done misfit, then it would be the normalized misfit that comes up in here. And here's the expression of the data misfit as a function of beta. And you can see it's coming down like this. So I'm really doing on it. And then it just kind of hits a little bit of plateau, and now you don't gain very much more as far as using this by reducing beta. So you just, but look what happens in the model more. So that's red. So over here it's small, and then it's stay small. But then once we get the beta in here, it really starts to reduce. So that's the character. If you take this and you plot it as a T-top curve, and you end up with a curve that looks like this. So here's where it's kind of like an L curve. So the expected value of so the number of data, for instance, is in here. You can see from looking at this curve that I bet you there's more signal I can get out of here, right? So you can reduce the misfit without changing the model very much. Anytime you can do that, keep going, because there's stuff here, and that may be actually important. And then, but you get to a point where you're like, okay, I'm done. I can't push this thing any farther. I need to stop someplace up here, because I know if I'm going here, I'm really starting to have structure just based on. Okay, so those things are crucial. They're not for every problem that we do, and you just want to keep in mind how this trade-off parameter, working, how it's affecting data misfit, how it's affecting the model norm, and at some point we're just going to be looking at different models that are here and making some assessment about, yeah, that's still looking okay, or no, that's not. Yeah, so I think we've kind of done this. Beta, here is beta. Beta is large, hardly giving anything. Beta too small, lots of noise, and beta all right, doing something. So in summary, okay, we solved the linear inverse problem when the model, when both things are L2, right? Both the misfit and the model objective function are L2. And then the solution, we can obtain it in one step, and we can choose the regularization parameter, as I talked about. But to address the non-uniqueness problem, we need to have a priority condition. And then now, what's the data? We've got the things that we talked about before, the structure, background model, geologic constraints, all of these things are possible. What I'd like to do now is to, out of this list of possible constraints, just kind of address, okay, how many of these can be put in, and let's not screw up the problem too much. Let's try to just keep it L2 and still solve it in one step. So let's look at crossable property. So here's the geometry. We've got some body in here. We're actually going to, as far as the model goes, it's going to be slowness, which is the reciprocal of the velocity. And that is because the travel time is the integral along the rate path of the slowness, so 1 over the velocity, times dl, which is the length. Yeah, so that's our real problem. And so m is actually slowness, but we're going to convert it back to velocity because it's too hard to understand. So here's our velocity model, and here's our data. Here's the travel time. Whoops. Yes. So we've got our equations, okay, for misfit, or sorry, for different norms. We discretize it, and then we can write it out. So the discrete form of all of these different velocity objective functions, we're going to have that. So here's, notice the alphas. So alpha s, that's pre-multiplying something that's, making all close to reference. Alpha x, that's concerned with derivatives in the x direction. Alpha z, concerned with derivatives in the z direction. So how do we choose these alpha parameters? Well, this is the thing that we're interested in. If you just kind of look dimensionally at what this is. So this is alpha s, and this is kind of like a delta m. It's squared in each area. And this is alpha x. Like that's a delta m, but over a scale of ls. So if we wanted to make this term here kind of equal influence to this term, we can see that the delta m squared that alpha s should be equal to like alpha x over some like squared. Okay, so that's a first order step in trying to say, well, these three things, I want to put them in. How do I do that? So we're going to scale up. So let's just take a look, see what happens. So here we're going to have a reference model, and we put alpha s with the numbers that we have. The scale length here, sort of like 10, 20 meters, something like that. So we just like, so that kind of is alpha s is 1 over 1,000. And just to the generic inversion, this is what we cover. So here's our observed data, here's predicted, here's the recovered model. This scale here, I'm not sure how well you can read the screen, but this is at an enhanced scale. It's 1,400 meters per second. So it kind of shows up. If we put it on the initial scale, same scale as this, you see how it's, you know, it's there, but it's weak. We've got something kind of in the right place, but it's smooth, it's smeared up. So if we, let's just take a look at exploring these different parameters. So this was our generic one that we just showed you with that kind of reduced scale. So LS is like 10 to minus 3. But if I just asked for something that was small, that was just close to the background was 1,000. So if I didn't care at all about smoothness, I get this. So again, I'm not quite sure how well you can see this, but it's speckled, right? It's got a lot of structure to it, ups and downs. It's not overly easy. I mean, you've tried to find a solution that's kind of as small as possible, as close as possible to 1,000 meters per second. But you haven't really done a nice job. Look what happens if you just say, oh, I like it horizontally smooth. Okay, but anything else? I'm just going to try to find something that's horizontally smooth. Well, you do that mathematically, get something like this. Look at the horizontal structure. I mean, all these things fit in data perfectly well. So they're just examples, not unique. And then if you try to do the same thing in the vertical direction, interesting enough, this problem, you still get a bit of vertical striking just because of the way everything was set for geometry. It's actually not so bad. And then you ask for just something that is smooth, but not necessarily close to a reference. You get something. So those are kind of examples of what you get. You've got parameters to play with. You know in principle what they're going to do, and this is an example in practice. Another thing that's I think informative is that when you have a problem and you're going to discretize it, discretize the inverse problem, then actually there's a regularization that can occur just because of your cell size. So if we get a cell size of 20 meters, for instance, then this is kind of what we get out. So it's kind of poor resolution, but actually this thing is a lot more stable. Condition number here is better. If we go to 10 meters, it looks like this. If we go to 5 meters, it looks like this. If we go to 2.5 meters, it looks like this. So this is kind of insightful also, in the sense that it shows you just like how my discretization of my problem can affect my end solution. And if you go to something that's really, actually, okay, here's a question to see if anybody really gets to get this. I'm really impressed. So you see all these lines that are coming in, okay? What do you think? What do you think they are, and why are they there?
Because there is almost no the lines between the receiver and the transmitters are not overlapping in one pixel. I mean, the probability of having intersection between these two lines in one of these small pixels is very low. So we are having like independent inversion for each one of those lines.
That's actually good. Anybody else? That was actually Yeah, so in the limit that you go to like really, really fine cells, okay, then yeah, each of those lines is essentially independent, and then the activated phase is just going to be, you know, a linear combination of those. So the final model you get out is just a linear combination of curve functions. Well, the curve functions are just not straight lines. They're kind of like this, right? So that means my final model is just going to be a bunch of lines that are coming out like that. And you can start to see that. So it's, you know, again, you know, like those things about kind of understanding, oh, my model, my activated space is just going to be a linear combination of curve functions, yes. You know, okay, I kind of get it. Good. Yeah, and then also you said this term here, right? So in one case you can say, well, sure, let's just put a reference model in, right? But the value that you pre-multiply that with is actually pretty important, because if alpha s is really small or not very big, then it just simply doesn't matter. So here's 3 inversions, one done with a reference model of 1,000. This one's done with a reference model of 750. This one's done with a reference model of 1250. So there's really not all that much difference when you look here. But alpha s is just 10 minus 3. If we make this larger and more important, then we should start to see models that go back to the reference model. And we can see what happens here. So we that tends to do this. So this is the true reference model. This is one that's really too low. Now it's really trying to compensate for that. It's trying very hard to make something that's close to 750 meters per second everywhere. And here it's 1,200. And so in this case, having a wrong reference model has hurt you. But you need to know, in order to make this term effective, that this number has to be large enough. Another thing that becomes important is just additional functionality of phi m by using weights. So here you're kind of now starting to micromanage, but you know, in these days when you're really trying to look at complicated systems and maybe trying to identify a small ore body or something else here, then looking at things at a smaller scale is important. So let's suppose we have got this thing here, and we've got 2 regions, one here and one here, and we want to find something out that is sort of sensible. So for instance, at W2, so in this region here, we want to make it close to a reference model. So let's suppose the reference model is blue. And this point here, we want to have a solution that's actually close to blue. Okay, so we could see this, have an internal weighting function here that could be at 2, it could be very large. So if WS is large, then it's going to try to make M very close to M round. And so the end result is that for WS is large here, your final model is going to look pretty much like the reference. Over here, however, you're in an anomalous zone. And so you're like, okay, relax things a bit. So you really don't want your solution to be equal to this background reference blue. You want to let it to be something good. You want to let it to whatever the data would like to choose. So you make WS really small here. So there's really no penalization for the difference, for the model to be different from the reference model. And then when it comes over to these guys here, so now if you think you've got a sharp jump, let's say in this region in here, you can make Wx small, right? Because then it doesn't penalize the jump. So you can use the L2 norm and still get up something that has got a substantial change across here. Whereas in this location here, well, sorry, this location here, Wz should be really large because you're still, you want variations in the Z direction. And here, you want variations in the Z direction, but not in X, and so you can adjust W's. Okay, so that's important piece of information because these are actually things that you can manage as you're trying to work with serious field examples and try to incorporate, what you know and what you don't know. And the reference model is important, but there'll also be some places where, I've got confidence in the reference model, or some places I don't have confidence. There are some places that I think I want to structure in a particular direction. You can manage them. And that turns out to be practically. So, so the summary here, so the character of the models are affected by these hyperparameters alpha, and the reference model, and the local weights. And one of the things you can do with these parameters is also change them around a bit just to explore model space, because that at least gives you a couple of examples of what the non-universe is. And so those are okay. Not sufficient though for some problems. The next is magnetics. So I want to just briefly go through this. So here's the 3D magnetic problem. So what time should they finish for lunch, or how does that work?
12:30 to 1 p.m.
Okay. Well, I'll kind of blast through. Yeah, well, I don't want to rush, as I said, but I'll slip through. Okay, so here we got a magnetic survey. So the thing that we're interested in is magnetic susceptibility. Magnetic susceptibility of rocks varies by many orders of magnitude. Perhaps people have seen pictures like this, but these are different kinds of rocks with orders of magnitude difference in susceptibility. Magnetite being a big hit on them. So the surveying method is as follows. So we've got, first of all, we need a source. So in this case, the source is the Earth's magnetic field. Okay? And now suppose that you're sitting up here at this particular point, and now the Earth's magnetic field is kind of coming in. So it's kind of coming in. So now bring it down to this picture here. So you've got Earth's magnetic field here, and now you've got a body that's sitting there that's magnetizable. The magnetization that occurs in this body is given by this formula here. The magnetization is equal to kappa susceptibility times H naught, which is the magnetic field. So that gives you the magnetization. This body then has its own magnetic field, right? So you can imagine, a body getting, here's the Earth field coming down here, the body gets magnetized in this particular direction, and it's got a magnetic field that looks like this. At the surface, we measure the total field. So that's the field of the anomaly plus the Earth field. So we measure this guy here, and then we want the total field anomaly, which means that let's subtract the value of the Earth field, and we can show that that result is approximately equal to the anomalous field projected onto the Earth field. Okay, so that's the essence of the magnetic experiment. Again, it's a linear equation. So we can have that our kernel functions now are just given by this. So we're going to take here, divide it up into these cells, and the elements of the Gij are just given by just one. So it's just volume that goes over a cell. Something. Okay. So that gives us our data in the form that we just been seeing it, but now it's a magnetic problem. So we got susceptibility, and here's our data. And for our example, we're going to use a block that's buried 50 meters below the surface, and it's 100 meters in each direction, and it's got a susceptibility of 0.05. We're going to do a survey. This is a very small survey compared to what people in ordinary. So the 100-meter line spacings, 25-meter station spacings, and these are the active data, added a bit of noise, for nanotesla's, something. So here's our model objectified. So that now seems, this should start feeling pretty familiar, right? So we've got a reference model, okay, which in this case, the background is probably going to be 0. We've got these smallness, smoothness X, Y, and Z. We've got these different coefficients, and we've got potential weightings in here. We've got a data mixture that looks like this. And because of the scale size that we have of our cell body, LX should probably be about 100. Okay. So now here's our inverse plot. We're going to set that up to minimize this function. And we're going to generate a 3D cube. And we're going to, this is, very small cube, 11,000 cells. And we're just going to find values of susceptibility to each of these that generates the data. And we only have 76. Well, here's the thing, right? And first time I saw this, is kind of like, this is depressing. Because you do all of this infrastructure work, you got the whole knowledge of the inverse problem down right, and then you go ahead and do the inversion, and you get something like this. So here's, can't really see that model is out there, and here's the inversion result. So it's like negative, positive, negative, but everything's at the surface. The block is supposed to be buried. Okay, can somebody tell me why that is expected? All of these ability. So, Julie tried to knock me out. Yeah, exactly. Why?
Yeah, I think that because it goes one. It depends on the distance, on the inverse distance. The shallower blocks are the data is more sensitive to the values that the sensitivity of the shallower blocks.
Perfect. So it's because of the sensitivity. Is it because you're aware of the equivalent surface result that comes from green spins? Yes. And what is it?
It's a linear surface distribution of source and adjust a 3D data.
So if you've got a potential field, so gravity data, magnetic data sitting above 3D, then you can actually reproduce those data exactly by having a layer of density or magnetic susceptibility that's infinitesimally thin and sitting right at the surface. So that's an equivalence. That's a fundamental mathematical non-uniqueness that just happens to exist, and and we're stating that here. So your comment was now 100% correct, because if you look at the kernel functions, then kernel, if you have a little dipole, it'll fall off as 1 over R cubed. Right? So if you look at the kernel functions, they fall, that sensitivity falls off this 1 over r cubed, that's the linear problem, to a log problem. Looks like that. So that is the heart of the problem. And even though you've done everything, like straight by the book, and the best thing you could do is like, so just to illustrate that, so here is, so here's a map, here's a magnetic map, and now what we're doing is trying to find an equivalent layer that reproduces that data. And if I put a layer in that significant chances of susceptibility is kind of comes to 9, but this susceptibility actually reproduces those data. I don't know why I didn't step through, but anyway, that's the end one. Anyway, we've got 4. It's kind of interesting because it shows what happens if you have layers at the surface or a progressive greater depth. You can actually reproduce something at the surface that looks pretty much like this, and it's an entirely different susceptibility. How did that happen? I have no idea. Okay. So anyway, come back to sensitivity, loss of information as a function of depth with that sensitivity. And we can fix it. I mean, we can try to do something. So because we know how the sensitivity falls on, let's just put an additional weighting into these guys here to kind of compensate that. You know, say, okay, if I'm a cell here or a cell down there, I kind of want to get equal probability, irrespective of the fact that the curve is. So I could do that. I could put that in here. And now look what I get. Okay, so this is hugely better, right? So I now do that sort of sensitivity rating, and now I've got something that's starting to look a lot better. I've got a Q in there as far as the difference between observed and predicted data. We clearly match that. So without sensitivity, it looks like that. With sensitivity, so that's looking pretty good, but it's not quite perfect. The good news is the structure is no longer concentrated at the surface. And at the main anomaly, we're trying to find the block, which is kind of there. But some of these negative values, or some of these blue values here, are actually negative. So that's not good. We don't know. And also the thing is smearing down in depth. So, you know, we kind of did a reasonable thing. We tried to do the sensitivity weighting, push things down, kind of good job us. But the odd actually kind of went down maybe a bit farther than it should, but even worse, it's got these negative values. So that means that what we want to do is now solve this problem with another piece of information, namely positivity. So our goal now is to solve this inverse problem, subject to the fact that the theta m is greater than 0. At this point, we've not changed the problem, seriously changed the problem, because we now have a non-linear problem to solve. So we've got, even if this is all quadratic, the moment that you subject it to any kind of non-constraints or positivity means that you've got to contend with a non-linear problem, and you're going to have to iterate and fix that. So that's kind of where we've been, and we're going to contend with that right after you guys have had some lunch, and we hopefully have our slides together. So just to reiterate, we started on the overview, then we tried to take you on a little bit of tour to understand, okay, with the overview you understand where the operations is coming from, and then look at the problem. Good job. Take it on curve, we're going to set up one formulation for how to do deterministic conversion. So we've got a mixed projective function and a model norm. The model is he is actually the portion that's flowing the car. He's the big guy. It used to be if people do inversion like, oh, I need some regularization or not. Now, the regularization is the important thing. Yeah, sure, it's a data function, but it's a regularization function, and information goes in. It's good. Now we understood a little bit of what was going on from SVD, just this whole concept of the mapping back and forth, but really there are only a few vectors here, each with their own particular shape, that play a role. And even with limited data, like we had 20, by the time you had a little bit of noise on, there was only like 6 vectors that were in each two. The rest of them, if you try to put them in, the noise is contaminating so much that you're getting more harm than good. So that was the role of that. And then the linear problem, we've now kind of stepped through. You've got the linear map, and you kind of play around with that. And now, so we showed that now 1D, 2D, 3D. And with 3D, then we get to like, okay, let's figure out more about what these alphas are, and maybe we need some more weightings. And, I mean, it's a little bit of manipulation and thinking, but you're thinking about it by understanding what's going on and what the effect is, and that's critical. And now we've got to the point where, like, okay, we've got as far as we can go. We're going to make this problem non-linear. So that's what we're going to come up. So this afternoon, not only are we going to address non-linear problems because of this positivity, but we're going to go back to most problems that we deal with that arise from partial differential equations end up being non-linear problems. And so that's pretty good. Okay.